先用中文。OK， 好，那我们今天呢，这个很高兴邀请到这个清华大学的洪乐文教授，那是这个应该是前任所长，对，然后呢来跟我们讲这个Federated Knowledge Education and In-Work Learning and Over Wireless Communications Wireless Networks。那 Federated Learning 是现在一个非常非常红的题目，那所以说这个其实虽然现在好像这个 AI 非常的红，可事实上呢，这个 AI 呢，其实他们都有个非常大的 network， 很强的 network 在 support 他们。就比如说，现在 ChatGPT 中国的复旦大学呢也想弄一个版本，结果1天之内呢网站就 crash 掉了，就是因为其实，美国 Google 他们呢其实有个非常强大的网络在 support 他们。那如何在 combine 这个 network design and the learning， 这个是个非常非常重要的一个课题。那这个我们这个洪教授呢是这方面的专家。那今天我们很高兴，他应该会给我们非常非常多这个可以做的方向。然后也许这个大家呢可以去往这个找题目的时候呢，也可以往这边走。OK，and yeah, because okay, Professor Hong want to train, want to talk in English, so let's welcome Professor Hong. Yeah.
谢谢林老师。那联系的时候本来想说有个外籍生，所以我就准备英文，希望大家不要介意。不过中间我都会讲中文，对，所以如果中间有什么问题，都可以用中文发问，我就再用中文解释这样。好，那就是谢谢各位老师出席，对，让我很紧张了。So the topic of my talk is federated knowledge caching and in-network learning over wireless networks. So this is just a self-introduction. My background is mainly in communication and signal processing. I've been focusing on topics related to beyond 5G and 6G. And I've also worked on some things related to IoT and sensor networks, especially regarding things like distributed detection, estimation, or some inference problems. Okay? But today, I mainly want to share with you two of my recent works. One is related to wireless knowledge caching in cellular networks, and the other is on in-network learning for Internet of Things. Okay? All right. So, as most of you know, in the past, most machine learning applications rely on this centralized data center to perform training of this powerful machine learning model. Okay, so this data center, right, often belonging to these industrial superpowers such as Amazon, Microsoft, Google, and so on, they gather data from their users and use this to train this powerful model. Now, this centralized architecture has worked well in the past, but really requires the users to sacrifice their own privacy because they need to send their personal data to this data center. Okay, so to overcome this privacy concern, a recent trend is to move towards a decentralized scenario. So in a decentralized setting, we hope to let users be able to train a local machine learning model using only its own data or data gathered from its trusted neighbors. And using this data, they can train a preliminary model locally, but through interaction with the central server, we hope that they can eventually converge towards a model that is, that achieves a inference accuracy that is almost as good as a centralized data center. Okay. Now, this is a very popular topic. It has been applied in many different applications. For example, in mobile applications, Google has used it in things like next word prediction or query suggestions. And you can also see many discussions in medical applications. So in medical applications, you may have a lot of these hospitals or health institutes that would like to train machine learning models to maybe perform image recognition or certain diagnosis without exchanging their patient's data with some centralized data center. Okay? Now, you also see a lot of this in IoT applications, because in IoT applications, you typically have these sensors deployed around the human environment, so they gather a lot of personal data that allows you to infer information about maybe personal behavior. Okay, so there's also a privacy concern here. Right. So, so this has been a really hot topic in recent years, but really how do you, do this decentralized learning, okay? So let me go through some preliminaries in case that some of you are not that familiar with this, right? So we know that in a typical machine learning problem, our goal is often to, especially for supervised learning, our goal is often to find the set of model parameters, let's say W. Okay, it's a little bit difficult to see the screen from up here. But anyway, so the goal is often to find a set of model parameters W that minimize some training loss function, let's say this capital F here, okay? So this training loss function helps us quantify how well we are able to predict a ground truth label using the input observation, right? And this is averaged over all points in our training data set. Right. Now this loss function can be a number of things. For example, in linear regression, this could be the quadratic error between the actual label and the predicted label. Or in a classification neural network, this could be something such as the cross entropy. Right. Now, if you have all the data available at a data center, you can compute this global loss function without any difficulty. And then to minimize it, you can apply any available optimization algorithm. Okay? So one of the most common is to use this centralized gradient descent, which is essentially, it's an iterative algorithm that is like rolling a ball down a hilly surface that is described by this function you're trying to minimize. So in this iterative algorithm, right, suppose that W of t is the solution that you get in iteration t. Then in iteration t plus 1, you try to perform an update by moving the solution in the direction of the negative gradient. And that will bring you a step closer to the optimal solution, W star. So if you continue to do this over multiple iterations, this will eventually bring you to the solution that you want, okay? Now, like I mentioned, if you have all of the data available at a centralized coordinator, then you have no difficulty computing this global loss function, and then you can apply any centralized algorithm, such as this gradient descent, to try to minimize it, okay? But in a decentralized setting, the data is instead distributed among multiple local platforms. And in this case, every client or local platform can only compute a local loss function, right, which is essentially this loss function, but averaged only over the data available at the local site, okay? Now, in this case, no single client will be able to optimize this global function by itself, so you will need to apply some sort of distributed optimization algorithm to try to achieve this goal, okay? So this widely popular federated learning framework can be viewed as a implementation, a distributed implementation of the gradient descent algorithm. Right. So the key idea is that if you try to apply this gradient descent update, right, which is something like this, right, the thing is that this global function, even though you are not able to compute it by any client itself, the thing is that this global function, right, can actually be written as a weighted sum of the gradient of these local loss functions. So this, sort of inspires a way to compute this in a distributed fashion. Right, the way to do this is that you start by, in each iteration, you start by having the coordinator send the solution in this current iteration, right? Let's say W of t. You send it to the local clients. The local clients use their own data set to perform a local update of these model parameters, send it back to the central server, which then aggregates them by computing a weighted sum of these local updates, okay? Now, if you plug this into this equation here, you can find that this update is actually equal to the centralized update given on the right, okay? So this is the main idea behind federated learning. Now, certainly there are many different variants to this, right? For example, some people may want to perform multiple local updates before they send it to the center to reduce the number of transmissions. But you know, we will not go into that today. All right. Now, in a wireless network, you can imagine that this will occur, this will typically occur between these mobile clients, let's say these cell phones or IoT devices or autonomous vehicles, and their edge server, which can be, you know, at the local small cell base station, at an access point, or some roadside unit, okay? So to train this machine learning model in a distributed fashion, you need multiple transmissions between these mobile clients and the edge server, right? And this will, you know, occupy a significant portion of the, you know, wireless resource, right? So therefore, it's important to, you know, determine how to schedule or to, you know, allocate the resources properly in order for this training process to be performed efficiently, right? So many people have looked at this problem, right? For example, people have looked at how to schedule these federated updates by taking into consideration multiple factors, such as the wireless channel condition, the data size available at the users, or the computational capability of these users. Right. So for example, in this toy example here, suppose we have 3 users, right? Each one with different data size and different computational capability, right? A laptop may be able to, you know, compute faster than, let's say, a cell phone, okay? Now, if there's no, if you do not do any, you know, special design here, a trivial implementation would be to have all the users perform their local computations in parallel, and then once everybody is done, you start to take turns transmitting to the central server, right? So you do this in every update round. But this is clearly inefficient, right? Because, you know, the time required for the users to perform the computation and communication differs drastically depending on their data size and computational capability. So, you know, if you take all of this into account in the scheduling, right, you could let certain users start to transmit, you know, while others are still computing. And you can even eliminate users that are causing excess delay to the update process, okay? So if you do this in every round, eventually the overall training time can be reduced significantly, okay? So this is, you know, using a toy example to sort of show how this scheduling or communication design can benefit the efficiency of federated learning, okay? Now, if you dig a little bit deeper into the physical layer, right, some people have also proposed to use the superposition property of the wireless channel to help perform this aggregation naturally over the air. So the way to do this is, you know, to let every user transmit a signal that is proportional to the local update that they're trying to exchange with the server, okay? So by sending this signal, right, these signals will arrive simultaneously at the receiver, aggregating in a way that emulates the, you know, aggregation that you would have wanted in this federated averaging algorithm, okay? All right, so these are, you know, some popular topics that people have been studying. Now, on top of these, you know, transmission or communication designs, what our group has been looking at is this, what we call the wireless knowledge caching framework, okay? So the key idea here is that, since all these updates will occupy so much of the, wireless resource, it is probably necessary to cache these models locally, right, at a local server or access point, right, so that it can facilitate, the access or the training of these models, okay, without always have to go through the backhaul to access the data center, okay. Right, so this is our key idea. Okay, so in this problem, right, we try to, among all these machine learning models, we try to determine, which machine learning models should be cached at which base station to minimize the cost or minimize the efficiency of training these machine learning models. Okay? But usually, the cache capacity at these local base stations are usually limited. So, you have to determine, because of this limited capacity, you won't be able to cache all the machine learning models. So you have to determine which models are most cost-effective to cache. Okay? So we start out with this single base station scenario. Okay, so suppose that the network consists of U users, and there are a total of capital M machine learning models with model sizes O1, O2, up to OM. Okay, and the caching policy that we want to determine is represented by these binary variables CM that is equal to 1 if, where CM is equal to 1 if we decide to cache the mth model, and is equal to 0 otherwise. Right? And the total number, the total size of the models that we cache must be less or equal to O max, which is the cache capacity.
Peter, sorry. So, yeah, I may ask for maybe the students, is that this is a two-tier network. So, indeed, you are a small base station and a more big, more centralized base station. Is it true? Such that the model is cached in the local base station. It's not in the user. Is it the model?
So we don't really talk about the macro base station here. Our goal is really to determine what models to cache at the local base station. Yeah. So
but finally, the model will be uploaded to the even centralized MBS. Is true?
No. We just train and cache the model locally.
Okay.
Yeah. So you could do a second tier of aggregation with the macro base station, but we don't consider that here.
Okay.
Yeah. Okay, all right, so our goal is to determine which models to cache, but we have a limited cache capacity. Right, so what are the factors to consider in making this caching decision? Right, so there are typically, 3 factors. One is user preference. We want to, cache models that are most popular. Right, so this is similar to the caching of multimedia content. Right, if certain YouTube videos are more popular, you want to cache those at the edge server, okay? Now, in addition to user preference, which is described by, the probability that each model is being accessed, we also need to take into consideration the local data set size, because the data set size sort of tells us how much this user can contribute to the training of this machine learning model, okay? And we also take into consideration the channel conditions and computational power because this impacts the latency of each update. Okay. Now, to perform this design, we need a design objective. Okay, so since we're looking at this machine learning problem, we choose to use a design objective that reflects the training, training effectiveness. Okay, the effectiveness of this model training process. Okay. Right. So following what we said at the very beginning, for each machine learning model M, we can define a global loss function, capital F sub M, which is a weighted sum of the local loss functions, and the aggregation that is performed in each iteration at the central at this edge server is also a weighted sum of the local updates. Okay, weighted sum of the local updates. Now, okay, so this is the local function, and this weighted sum has a weight that depends on how much data is available at the user, which is user U in this case. Okay. Now, similarly, in this aggregation, right? In this aggregation, you take a weighted sum of the local updates, where the weight depends on the data size at the user. But in practice, when you're transmitting over a wireless network, due to limited transmission resources, usually not all users will be able to participate in the training process. Okay. So to take that into account, we further introduce this user selection variable S that is equal to 1 if we decide to select user U to participate in the training, and is 0 otherwise. Okay? So we allow for this user selection to decide which users should contribute to the training process. Now, a user not participating in the training process can still access this model if it needs to. Right? We just don't want it to, participate because it may cause access delay. All right. Okay. So under certain, relatively ideal assumptions on the loss function, you can obtain a training error bound given here. So this is a bound on the difference between the loss that you get through federated learning and the loss that you would have obtained with centralized training. Okay. Now this upper bound is a little bit complicated, so we don't want to use this for design, but instead we simplify it a little bit by first letting the number of iterations mu go to infinity. All right, this will allow us to reduce the formula a little bit. So this upper bound here is what we call the extremity error bound. Right? So we're going to use this as the performance measure later on in the simulations. But instead of trying to minimize this extremity error bound, we find that this bound actually increases monotonically with this value here. Okay, so if it increases monotonically with this value, this means that minimizing this value equivalently helps us minimize this bound. Okay, so from now on, we're just going to look at this factor here as our design objective. Now, what is this factor? If you look closely, this is just 1 over dm, which is the total amount of data for model M, times the summation of dmu, which is the data available at user U, okay, times 1 minus SMU. So 1 minus SMU, right? This is equal to 1 if the user U is not selected. So what we're summing here. Right, what we're summing here is the data that is lost, right, by not selecting these users. Okay, so we call this the proportional data loss. Right. Now, in an ideal world, if you want to minimize the proportional data loss, you just try to choose, let all users participate in the training. Okay, but this is not possible due to constraints on the latency and energy. Okay. So here we're going to consider constraints on, both transmission latency, computational latency, and energy consumption. Okay. So on the top, we have the downlink latency, which is the model size divided by the transmission rate of the users, maximized over all users that are selected. Okay. Then we have the uplink latency, which includes the uplink transmission time plus the computation time at each user, right? Also maximized over users that are selected. And then we also have the energy consumption, right, which includes the transmission energy and the computational energy. Okay. So, right, to sort of summarize, we take the proportional data loss as the design objective, right? We try to minimize the data that is lost, but this is subject to constraints on the latency and the energy consumption. Okay. So our optimization problem can be formulated as follows. Okay, so these are some details. So our optimization problem can be formulated as follows. So what we do here is we try to minimize an average of the proportional data loss, right, averaged over the user preference, okay? Now, if a model is cached at the local base station, this means that the users can participate in the training of this model. So the data loss is given by this, which is the loss of, of the few users that are not selected, okay? But if a model is not cached at the local base station, then, there's no model at the base stations for users to jointly train, right? So if you need this AI service, you would have to train the model locally using only your own data. So almost all the other users' data are lost in this case, okay? So, right, so this you can just view as the average proportional data loss averaged over, the user preference and whether or not you cached the model at the local base station. And you try to minimize this subject to a constraint on the latency, a constraint on the energy consumption, the power and bandwidth constraint, which is the wireless resource that is available, and the cache capacity constraint, right? The number of models you cache cannot exceed the cache capacity, okay? Now this optimization problem is looks a little bit complicated, but there's a way to solve this, okay? So without going into the details, just to give you an idea of how we solve it, so the thing is that, if you first assume that a model is cached at the local base station, then you will be able to, compute the resources that is needed for each user to participate in the training. And then based on that, you can perform user selection, okay, based on the latency that you can tolerate. Okay, so you first compute the minimum resources required for each user to participate in the training, and then select users, as many users as you can, given the latency and energy constraint. Okay, and then once you obtain this optimal user selection result for each model, you can then perform a knowledge caching optimization, right, over the caching variable C, and this will result in a simple 0-1 knapsack problem. All right, so this is just to give you an idea of how this can be solved. Okay. Now, what we do next is to extend this to multiple base stations. Right. So previously we assumed that we have only one base station, and now we have multiple base stations. So the thing with multiple base stations is that now there's an additional problem of user association. Right? So now instead of in addition to deciding which models to cache at which base station, you now further need to decide, which base station each user should be associated with. Okay? So on the one hand, you want a user to be associated with the base station that is close by because the transmission condition is more favorable. But you also want to associate it with a base station that has more users with the common interest as yourself, right? So if you have more users associated with the base station that would like to access the same model, then potentially you can have a more reliable training performance on that model. Okay? All right. So this user association now is coupled with the caching decision. Okay, so this makes the problem a little bit more difficult. Okay. This user association is actually coupled with the user selection, right? So your user has to be associated with the base station in order to be selected to participate in the training process, right? So, without going into the details, you can model this similarly. The difficulty really lies in this coupling between the user selection and association. Okay, so, to solve this problem, so just to give you an idea of how you can solve it, we just include this constraint, we introduce a Lagrange variable to introduce this constraint into the objective, okay, and then apply a dual gradient method to solve it. So the good thing is that when you are given the Lagrange parameter, right, solving the other parameters reduces to an algorithm that is very similar to the single base station case. Okay. All right. So let's look at some performance curves. Okay. So here we have the extremity error bound, right, versus the cache capacity. Okay. So we compare between 3 caching policies: random caching, preference caching, and our proposed knowledge caching scheme. Okay. So obviously, random caching is bad, but preference caching is what you would do with multimedia content, right? You try to cache models that are most popular. Okay. So here, the top curves are the case that apply only equal resource allocation. The bottom curves are cases where you apply optimal resource allocation. This is random caching, preference caching, and our proposed scheme, right? So you can see that our proposed scheme achieves a smaller extremity error bound, but the gain really reduces as the cache capacity becomes larger, because in this case, you would probably be able to cache most models anyway, okay? Now, on the right, you can look at the extremity error bound versus the zip parameter. Right? The zip parameter is what we're using a zip distribution to model the user preference probability. And as the zip parameter increases, this means that the user preference is more concentrated among certain models. Okay? So the user preference is really extreme when this zip parameter increases. So, when the user preference is really concentrated, then the policy using preference caching and our proposed caching scheme really does not have much difference, right? Because you just cache the most popular model and that's it. Okay, but if you have a more not as extreme case, then our scheme will have a bigger advantage. So you see a similar trend here in the multiple base station case. But just one thing I would like to mention is that in the multiple base station case, as you increase the zip parameter, right, making the user preference more concentrated, the preference caching still does not perform as well as our proposed caching. And this is because in this curve above here, we're using the nearest association, right? You're just letting the user associate with the nearest base station without taking into account, which other users are associated with this base station, okay? And that's bad, right? Okay, right. So this is the first work that I wanted to share. Now, in this previous work, we focused on federated learning, right? So in federated learning, a basic assumption is that all of the mobile clients are able to cache, to store and process a full machine learning model. Okay. Now, this is maybe possible in certain mobile applications, but this would not be possible if you're looking at things such as Internet of Things or wireless sensor networks, right? Because in IoT and sensor networks, these devices are very simple. They have small storage and small computational capability, right? So if the devices are not able to process a full machine learning model, then what do you do? Right, so this is the answer. This is the question that we're trying to answer. Right, so the framework we propose is what we call a in-network learning framework. Okay? So the key idea is like this, right? So like I mentioned, in IoT and wireless sensor networks, right, we have a bunch of devices deployed in an environment, right, to gather information. And then you would like to, use this information to perform inference on, on what's happening in the environment. So you can either, send all of the data back to a central server, which may, require large communication overhead, or you can let the sensors do some computation. Right? But the sensor, each sensor by itself is very simple. It won't be able to do very complex computation. But the key idea here is that, even though each sensor is only able to do very simple computation, maybe just a few, with a few neurons if you're looking at a neural network. But if you put them together, look at them as a whole, then they can potentially form this complex, this large, deep, complex neural network that can help you perform complex tasks. Okay, so this is the idea. Okay. All right, so this is pretty simple. So suppose that we have, the way we do this is as follows. So suppose that we have a bunch of sensors, each one only able to compute a small neural subnetwork, and we place them into different groups, okay? So we partition them into different groups. Now, the first group, we call the source group, is responsible for making observations from the underlying phenomenon, right? So suppose these gather information from the environment. They perform a little bit of local processing and then pass it to the next group, which we call the relay group. Right? This relay group receives the information, performs further processing, and then forwards it again to the next group. So you do this through a few relay groups until you reach the final group, which we call the destination group, which takes the received signal and then outputs the final inference. Okay? Now, this is a very simple idea, right? Now, the thing is that, when doing this, you can imagine that there would be a, incredibly large amount of information to transmit from one layer to the other, okay? From one group to the other. So instead of applying, okay, so I said this already, right? So instead of applying a classical, digital transmission where, each sensor take turns in transmitting to sensors in the next group, we adopt a intergroup aggregation using the so-called over-the-air computation, okay? So the idea is to let the users, let the sensors in the same group transmit simultaneously over the same orthogonal channels, okay? And let their signals naturally aggregate over the air while they arrive at the sensor in the next group, okay? So we can look at the operation between two layers here, okay? So suppose that for sensor K, right, let VK be the input of its local neural subnetwork, and let UK be the output of this local neural subnetwork, okay? Now, assume that we allocate TL orthogonal channels for the transmission of sensors in this group, in group L, okay? So we allocate a total of TL channels, you can think of them as time slots, for all the sensors in group L, okay? Now, the output of each neural, of each local subnetwork is this UK here, right, which has dimension, I think we call it OK. Let me see. Yeah, okay. Right, so the output of this local network, suppose it has dimension OK. Now, in order to convert this local output into the TL dimensional signal that should be transmitted over these TL channels, what we do is that we design a TL by OK transmit filter so that by multiplying this transmit filter FK with this local output UK, we convert it to a TL dimensional signal we call UK tilde, and then we transmit this UK tilde over these TL channels, okay? So each sensor in this group does the same thing, and then when they transmit simultaneously, the signals will naturally aggregate at the receiver, okay? So the signal received at sensor SK prime in the next group is the summation of the signals transmitted by sensors in the previous group multiplied by the channel matrix plus noise. Okay? Now this transmitted signal UK tilde is just UK times the transmit filter. Right. Now this received signal is with dimension TL. Now to convert it to the dimension of the input of the neural network, we need to further multiply this with a receive filter GK prime, okay, to convert the received signal to this VK prime, which is the input of the local neural network. Okay. Now, if you look at this, right, if you look at this formula here, you can see that from UK to VK prime, right, they experience a linear operation described by the combination of GK prime, HK K prime, and FK. Okay? So if you combine these three together, G, H, and F, you can form an effective weight matrix, WK K prime, that connects the output of this local network here to the input of this local network here. Okay? So this WK K prime is like the neural network weight that you would be using in between these two layers of the neural network. Okay. Now then the remaining question is, how do you design the transmit and receive filters? Okay? So we propose two approaches to do this. Okay. So one approach is what we call the MMSE-based design. All right. So what we do here is that we assume that we can train offline an ideal neural network of the same architecture, okay, that is noiseless, right? We designed this ideally, that has this VK prime star as the input to the local neural network of the next group, okay? And we try to design F and G such that the actual input, okay, is close to this ideal input. Okay, so we train an ideal network offline, and we try to, find F and G that lets the actual input be close to the ideal input. Okay, so if you plug everything inside, you can write this mean square error explicitly in this form, right? And then you can try to minimize this mean square error, in an alternating fashion by optimizing over F and G interchange in turn, okay, until convergence, okay? So doing this in turn, the advantage of doing this in turn is because is that when you fix G and optimize F, or if you fix F and optimize G, you get a closed form solution. So you can do this really fast, okay? Right. So if you fix G, then you have a closed form for F. If you fix F, you have a closed form for G. Okay. So a disclaimer here is that so this F here is not exactly closed form because there is a Lagrange parameter here that we need to find to satisfy the power constraint. But you can also do that easily using a bisection algorithm, right? So overall, this MMSE algorithm is easy to implement. Okay. Now, another approach is to just directly train the entire network end-to-end over the air, okay? This is pretty simple, okay? But actually, the difficulty lies in how to obtain the transmit and receive filters here when you're training end-to-end, okay? So to find the transmit and receive filters, we further incorporate what we call a transmit filter net and a receive filter net, right? So the transmit filter net takes the outgoing channels as input and then produces this transmit filter matrix for use that you use to map UK to UK tilde, okay? And you do the same thing here, right? You use a receive filter net to produce this receive filter matrix GK prime, okay? All right. So we can later on take a look at how this performs, right? So we have two approaches. One is the MMSE-based solution, and the other is obtained by end-to-end training. Now, up to this point, we have assumed that we already know which sensors are in which group, okay? But in practice, in a sensor network scenario, you probably just, deploy all these different sensors in the field, right? And you try to let them self-organize into groups. But in that case, how do you determine which sensors should be in which group? Because deciding on which sensors in which group affects not only the channel condition between sensors in adjacent groups, but it also affects the resulting neural network architecture, okay? So we have a method for performing the group assignment, okay? So I'm going a little bit over time, but just to give you an idea of how to do this. So the question here is, how are the sensors assigned to different groups, okay? So our key idea is to find this through network pruning, okay? So initially what we do is that we first let all the sensors be associated with every group, okay? So if we have, let's say, 20 sensors, we just let all 20 sensors be associated with every group, okay? And when the sensor serves the role in a different group, you can allow it to take on different neural network weights. Okay. Then, right, starting out from this ideal scenario, we start to prune the sensors from each group, right? So, so in each iteration, we prune a sensor from one of the groups that it is associated with. And we decide which group to prune based on how effective this sensor is in that group, okay? So I don't want to go into the details of this, but you can measure this effectiveness through a measure on, let's see, okay? You can determine how effective the sensor is in that group by measuring the strength of its outgoing weights to the next layer, okay? So you can do that iteratively until each sensor is associated with only one group. Okay. All right. So here we have a simple example. So first, we assume that we have only 7 sensors, and we already know that 2 are associated with the source group, 2 in the first relay group, 2 in the second relay group, and 1 in the destination group. Okay. And we compare with a centralized model that has an architecture equal to the combination of all these sensors. Okay. All right, so these are the simulation parameters. All right. So here you can look at the test accuracy versus SNR. Okay. The top dashed curve is the ideal case for the centralized model. This black curve is the baseline, which is obtained through a truncated channel inversion scheme for the transmission. This scheme is often used in the literature. And the 3 curves in the middle are our proposed schemes. Okay, so the blue curve is approach 1. This sort of purple curve is approach 2. Okay. Now, the difference between these 3 curves are that we increase the number of time slots assigned to the intergroup transmission. So this corresponds to the least number of time slots, and this corresponds to the most number of time slots. So you can see that as you increase the number of time slots, the users are able to more capable of combating the channel fading and noise, and therefore performs better. Okay. Now here you can look at the test accuracy versus the number of time slots, okay? So you can see that when the number of time slots is sufficient, everybody performs pretty well. But when the number of time slots is not enough, right? When the number of time slots is not enough, you can see that approach 1 actually degrades rapidly, right? So this is because in this case, you do not have sufficient dimension for your transmit and receive filter to approximate the ideal weight that you want, okay? But end-to-end training still is pretty robust because it can sort of readjust their weights to the lack of transmission dimension, okay? Right. So that's about it. So this is this is some example for applying our group assignment strategy. So without going into the details, you can sort of see that proper group assignment is really essential to the final testing accuracy, right? So you can see here that for our proposed group assignment strategy, you can achieve a very high inference accuracy, but for other baselines where you assign the sensors either based on sensor coverage or on the size of these groups, they both perform pretty bad. Okay. Yeah. All right. So that's all. So today my main goal is really to introduce two of our recent works. One focusing on cellular networks and the other focusing on IoT networks, and really to show through these examples how the communication design can impact the effectiveness of AI and machine learning in the application layer. All right, thank you.
Okay, thanks, Peter. Okay, sorry, I forget to mention that Peter is already a distinguished lecturer for Computation Society, which means that if you doesn't listen to this talk in NTU, you may need to pay money. So it saves some money for you and your advisor. Okay. So any questions from the student? 学生有问题吗？OK， 那我用，
那个 Peter， 所以刚刚在第二个 work 里面，你们在训练那个 end-to-end 的这个 distributed 的这个 network 的时候，它那个 channel 的的条件是它是固定的吗？还是说它是非零的？就在每个 epoch 在训练的时候，它是怎么跑的？
它是改变的，对，它就说就是说我们是让它 random 在改变的这样子，对。
所以每个 pass 在做 back propagation 的时候，它都是会改变的。
对，因为其实我们就是有去train 一个这个，主要就是我们有去 train 这个 transmit 和 receive filter 去 adapt to 这些channel variation 这样子。对，那其实我们也有试过，就是说我们不去做这个 adaptation， 就是说你 train 出来的 neural network 就是会 average over different channel realization。对，这个也是可以 work to some degree， 但是就是没有那么好，因为它就没有真的利用到 channel knowledge 去compensate。
OK， 就是说你是知道 channel state information 的，然后用那个去做这个训练这个 filter 的动作这样子。
对。其实我们现在也有在做，就是说，因为这里是 ideally 知道你已经知道这个 channel realization 是什么，那其实也是没有真的需要那么强的假设，就是说你也可以假设你传过来的多留一个 symbol 做 pilot， 然后它这个的 receiver 呢就直接拿 pilot 跟收到的东西自己去学怎么 combine 这样子，对，这也是可以做的还不错这样子。
那训练的这个结果就是说。所以它对于这种就是非零的模型，比如说它如果是有很剧烈的，比如说它会断线，以至于说它会完全连不上的状况，让你的这个 network 的结构大幅改变的话，我想你们应该是用假设是 relay failing 或是 Rayleigh failing 的模型在做验证的嘛。那如果说是这种比较就是剧烈的这个断线的情况的话，会不会有影响？因为感觉这种很 discrete 的情况会有很大的影响。对，
这是很好的一个问题，就是说如果就是你简单来讲回答的话，就是说你如果要对抗这些问题的话，你可能就是 train 的过程中就是要考量进去这些robustness 的 issue 这样子。但是我们在这里一开始是就是没有假设断线，就是这种像你说 relay failing、Rayleigh failing 但是我们后续也是有看说比如说你有 random 的 probability， 有些人断线，那这个其实很像是一个 dropout 的 training 这样子，对，所以你的 network 就会 train 的比较 robust 这样子。对，那其实我刚忘记讲，就是说我自己很喜欢这个想法的另外一个地方，就是说它其实就好像是说你这些 sensor 好像就是可以任意的模组化，这样就假设你买了10个或者20个 sensor， 然后你可以随便的这个排列组合呢，可以 reconfigure 出不同的这个 network 的 architecture。对，那为什么后面的 group assignment 很重要？就是说我现在这个环境，我可能一下子要做这个人脸辨识，然后一下子要做这个火灾的侦测或什么。那你透过这个 group assignment strategy， 你就可以因应不同的 application reconfigure 出不同的这个 grouping 的 strategy 这样。那其实再下一步的话，就是我们现在在看的，就是说类似那个 lifelong learning， 就是你如果说有一个就第2个 task、第3个 task、第4个 task 进来，那你是不是只要多撒一些 sensor， 它就可以越来越强大，然后就是任意的不同的 application 去 reconfigure 这样子，对，不过这都有一点实验的 study， 比较没有太多 theoretical 的这个的基础这样。
那还有问题吗 ？OK。
就刚刚有讲到，就是好像是复旦还是大陆的某间大学最近有在做这个相关的研究，然后就是 crash 掉。那可以请问一下教授，这个有点跑题，可是可以请问一下教授，就是认为说这个东西 crash 掉的点可能是在哪里，或者说有什么想法这样子？对。
不然我 comment 一下，但是我这个
对，
我自己刚才自己在开场的时候临时想到，就事实上就是说，其实比较像是那个刚才那个王教授讲的，就是说，其实你这个network crash 就可以视为你这边 sensor， 然后呢整个就坏掉了，或者是说，因为毕竟 sensor network energy 可能很低，它被用掉，它就直接 off 掉了。对，那应该就是要如何去整个 network 要 robust these two。当然，我觉得实际上来说，工程上来说，我们没有办法去做这个 complete failure， 就是所有 sensor 都烂掉，那当然就什么都没办法做。但是有没有说大概有没有可能？其实我觉得这是很困难的题目，就是有没有可能说这个 network 啊，假设比如说我们可以保证它，比如说80%还 alive，80% 或者是90% alive， 而 still can be function， 也许这样子在您这个work 里面有没有办法做这样的 extension 这样子？也许把它翻译成这个问题，也许会比较符合你的这个 direction 这样。
对，所以谢谢连老师。那我觉得这个有点像刚刚王老师那个问题，就是说我可能有些 node fail 的话，就是说你如果要考量这个情形的话，你在 training 的过程就要把这些几率考量进来做 training 这样。那你像我刚才说，这有点像 dropout 的这种 training 的方式，它就会让你的 network 比较 robust 这样的。对，那其实您刚才那个问题，我觉得可能比较不是说真的是什么 node 就坏掉，我觉得它应该比较像是就是这个 job 太多 congested 这样，就是它就是处理不来，你就一直在那边排在那个 queue 里面这样，对。
那 congestion control 你就大家都塞那边这样子，对。可是因为那可能跟你这边的 work 是不太一样的，那是 QE model 的事情，就对了。
谢谢。
OK， 那很好。那学生还有别的问题吗 ？OK，
记得哪页？16。OK， 这个吗？
这3个好，谢谢。喂，这3个 device 它不是 independent 的吗？那它的齿轮应该直接跟那个天线的符号接在一起啊，它们为什么要接那么开呢？
所以这个first of all， 这个是一个 toy example，OK， 那 所以说你如果说不去特别做设计的话，你可能就是说通常会等大家算完以后，然后才开始 update 这个资料。OK， 那这个当然就是像您说的，这很明显就是不 efficient 嘛。Right， 所以说你可能就是你先算完的人可能就可以开始做这个传输，你不用把 computation 跟 communication 这两件事情分开来做这样子。对，
那个齿轮就是计算嘛，那个天线就是 transmission，
就开始算这样子，对。
算完马上就直接 transmission 了，中间一大堆空白的，不是很浪费？
对，你说的没错啊。所以说，就像您说的，就是聪明的我们就是可以这样子做，这样子，对。
我是说中间就完全不要有空白的了。
哦，你是说这里吗？那这个 depend on 你有多少的那个 bandwidth 可以去传哦。就是你如果是只有一个通道的话，那大家当然要轮流传这样子。
好
，OK。
你有问题吗？
我们今天时间也差不多，那谢谢这个赵老师，那有兴趣的人可以私下分享。
好，谢谢大家。